spectra, looking at the colors of light absorbed and emitted by atoms, and looking at Rutherford scattering, which I'll explain in a minute. So the atomic spectra, the idea is if you take a source of light like a lamp like this, you guys turn the room lights off. You take a narrow lamp like this and pass the light through a prism or through one of these diffraction gratings. If you look at it, you'll see colored images off to the side, and you'll see sort of very discrete lines. Right? You'll see, I'll black the screen. Right? You see there's kind of a reddish line. There's a sort of blue-green one, and there's some in the purple. And there's kind of, if you look, there's some really faint stripes, but if you look at this, you see a very particular set of colors. All right, what this is some hydrogen gas that's in a tube. It's being excited so that it emits light, and that's characteristic of hydrogen. Now, if you take a different element, right? So here's hydrogen has there's a very bright red line, there's a blue-green one, and there's some lines in the blue and the purple. If you take helium, for example, helium also has a red line, but it's at a different wavelength. Helium's got some yellow and some green showing up, and there's a more complicated structure. If you take nitrogen, nitrogen has this huge smear of lines that are all over the place. Neon is the other one that's on here. Neon is, has a whole bunch of lines. They're mostly concentrated in the red. That's why your neon light, the traditional thing, has that orangey red color. It's because it's emitting all of this light that's concentrated down in the red and yellow region of the spectrum. If it's heated or you pass an electric current through it, you do something to dump a lot of energy into a gas of atoms of a particular element, you can make it emit light, and this shows up. So one of the traditional ways to do this is like chemists will do flame tests, right? You take a little bit of something and you stick it into the flame of a Bunsen burner, and the flame will change color, and from the color change you can say something about what's in there. Yeah.
So when we're using this for the heat of the stars that's causing pollution?
Right, so if you're looking out into the universe, you see stars are hot, and you'll see either, in some cases, you'll see bright lines of emission if a star has a lot of a particular thing. What you see more in stars is actually absorption lines. You see at the same frequencies, at the same wavelengths, you'll see a dark spot. You'll see some of the light that should be coming from the star is missing because it's been absorbed by atoms of a particular element. And so this is figured out in the 1860s. As people like Fraunhofer and Kirchhoff noticed that this happens, and they noticed that every element known to science has its own unique set of these frequencies, of particular wavelengths and frequency at which it will emit light or absorb light, and that you can use these to identify elements. By 1870, people are finding new elements by saying, I have this sample of ore, I heated it up, I got a color of light out that doesn't correspond to anything we know of, therefore there's a new element here. Right? By the 1890s, the element helium is called helium because it's first discovered from a spectral line in the spectrum of the sun that didn't correspond to anything else. So they identified this as a new element, and they called it helium after the Greek god of the sun. So really useful fact. Completely mysterious. And nobody has any idea why this happens. All right. In the 1800s. Quickly identified as a useful thing, not quickly explained. The key to the explanation ends up being this hydrogen that we have in the little lamp here, because it has a really, really simple spectrum. All right, it's got, in the visible region, there's sort of 4, maybe 5 lines that you can see. There's this red one, the sort of blue-green one, a deeper blue and a purple. And if you're really careful about doing it, you can find a few more. And there's this pattern that shows up. There's one at a long wavelength, and there's a big gap right? A shorter wavelength. Then there's a smaller gap to the next one, smaller gap to the next one, smaller gap to the next one. And there's a very regular pattern to this. Right? This pattern, a couple of people, Balmer was actually a school teacher, just playing around mathematically with the measured frequencies of these, found a relationship between these frequencies that said, you know, you can relate the wavelength to some constant of nature that nowadays we call R after Rydberg, who put the equation in this form. And then you just assign a couple of integers to each of these lines. So n1 and n2 are, you know, 1, 2, 3, 4, right, and so on. And you can relate the frequency to a difference between these integers. And this turns out to work brilliantly. If you're talking about the visible spectrum, you pick one of those numbers, say n2, you call that 2. And then n1 can be 3, 4, 5, any number you like. And there are lines that correspond to each of those combinations. Yeah.
So does that matter which direction you're numbered, or any particular number you have?
You want, so if n2 is 2, you don't want this to be negative. So if, you know, n2 is 2, then n1 needs to be 3, 4, 5, 6, and so on. And if, you know, if n2 is 1, then n1 can be 2, 3, 4, 5, and so on. But there's this very simple pattern, right, that shows up mathematically. And this turns out to work for an enormous range of frequencies. This happens not just in the visible part of the spectrum, but the exact same formula works to explain. I'm going to plug my laptop into a different spot so I don't keep tripping over the cord. The exact same pattern works in all different regions of the spectrum. Okay, so this is actually on a logarithmic scale. And this is the ultraviolet, here's the visible, here's the infrared, you know, deeper infrared, down into the microwave and radio sort of ranges. And they all show the same pattern. So this is visible here. They all show the same pattern. You have a line at a long wavelength, and then a big gap, and then there's a smaller gap to the next one, smaller gap, and so on. They all get together. And all of these are fit nicely by this single pattern, mathematical pattern. Right. This kind of thing is really enticing to particularly theoretical physicists, because you look at this and you say, it's a really simple pattern. There must be a really simple rule that explains it. All right, so people are trying to figure out, okay, hydrogen, this is a good place to look because it's got a really simple pattern. There must be some simple rule that underlies this. And so people try to figure out, how does this happen? Okay. So how does this happen? Well, right, we know, in the late 1800s, everybody knows that light's a wave. It's made by, it's an electromagnetic wave. It's made by moving charges. So if you have an electron, you wiggle that electron back and forth. That makes a wave that travels out from that electron. Or if you have a wave, comes in, that electron sitting there, it jiggles the electron up and down, and that does something to the atom. All right. So there's this relationship between moving charges and light. So, all right, you want to make a model that explains atoms emitting light of particular frequencies. You say, well, we know that atoms contain electrons. So there's an atom represented by the green circle, and there's some electrons inside it. What the green circle is, we don't know, but it's got to be positive because atoms don't have an electric charge, so there must be the same amount of positive charge there as there are negative charges from the electrons. So there's some positive stuff. And those electrons are stuck in it in some way. And those electrons, can vibrate back and forth. And they vibrate back and forth like they're held in by a spring that has a particular frequency. Right? And so these one electron in there gives you the red line, and maybe there's another one that gives you, a longer wavelength, and maybe there's another one that goes really fast that gives you the blue. And that's sort of the conceptual model that you have to have in the late 1800s for this, which is not especially simple and satisfying. right? There's a huge number of steps there where I am waving my hands madly and saying, well, we don't know what the positive stuff is, but there's got to be positive stuff there, so let's just say there's positive stuff there. And we don't know what's holding the electrons in place, but they've got to be held in place because they're not running away. So, this is semi-derisively referred to as the plum pudding model because the electrons are like raisins embedded in a plum pudding. Not a real satisfying model, and it gets a whole lot worse in 1909. And 1909 is the other experiment that I mentioned at the beginning. It's called Rutherford backscattering, but it was actually done by these two guys. So this is Ernest Marsden, who is from New Zealand, and this is Hans Geiger of Geiger counter fame. He later went on to invent the Geiger counter, but he started out working for Ernest Rutherford. They were detecting particles in experiments with radioactivity by having a particle hit a screen where it would then fluoresce. But the fluorescence is a very dim little flash of light, and so you had to like peer through a telescope and count how many of these little dim flashes you saw per second, and it was this really tedious, really hard to do thing. You'd have to sit in the dark for hours to let your eyes, fully adjust, and then concentrate really hard on counting things. Miserable work. So Geiger invented the Geiger counter to do this a little more automatically. So anyway, so what these guys are doing, they're doing an experiment in the lab of Ernest Rutherford in Manchester, England. Marsden was actually an undergraduate student. And they were taking alpha particles and firing them at a thin sheet of gold. And the idea is they're going to look at the alpha particles are going to go in. The gold is made up of atoms. The alpha particles are going to interact with the atom in some way, and they're going to be deflected from their original path. All right, and the idea is, well, we measure how much they deflect. That's going to tell us something about the structure of the material that they're passing through. And so they know that alpha particles will go through. If you make a very thin foil of gold, alpha particles will go through it. And then they're going to look at, if we have the gold, if we have nothing there, we have a little spot. If we put the gold foil in, the spot's going to get bigger because things are going to get deflected, and that deflection will tell us something. So this is a straightforward experiment. What happens, though, is something that takes them completely by surprise. All right, what they see is, mostly alpha particles go through and deflect a little bit on the far side, but every now and then, one bounces straight back. All right, comes in, and they see alpha particles on the same side of the gold foil as the source. And that shouldn't happen, right? Because they're using a very thin foil of gold, right? And very high energy alpha particles. The alpha particles should just blast right through there. Maybe they deflect a little bit, but not much at all. This is one of my favorite quotes in the history of science. This is Rutherford describing this after the fact. It says, "It's quite the most incredible event that has ever happened to me. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." All right, that's how startling it is that these things come back. And the reason for that is that if in this sort of plum pudding model where you're shooting an alpha particle in, the alpha particle should just go, you've got a great big atom, the alpha particle should just go right through that. Right? The only way you can explain this backscattering is if you have not a great big diffuse positive blob with some little electrons inside, but if you have the vast majority of the mass of the atom concentrated in a tiny little solid point in the center of the atom. And that's the only way you can have, otherwise you can't make the energy and momentum work out. Right? So in order for something to bounce straight back from it, you throw something at a target, in order for it to come back, the thing that it hits has to be much heavier than the thing that you sent in. Right? If you have a bowling ball sitting on the ground and you throw a ping pong ball at it, the ping pong ball will come back at you from the bowling ball. The reverse is not true. Right? If you have something really, really light, you throw a bowling ball at it, the bowling ball doesn't slow down much. The light thing takes off at high speed. Right? And that's what everybody sort of expected would happen, but that's not what happens. All right, what you see is telling you that there's a very heavy, very solid thing in the center of the atom. Yes?
Maybe you explained this and I missed it. What is the alpha particle made of?
Alpha particle is, at this time they knew, Rutherford had actually gotten a Nobel for showing that it's the nucleus of a helium atom. And so some heavy elements, in particular radium, when it decays, will spit out a radioactive particle that they called out. Rutherford gave it the symbol alpha, and it stuck. And those come out, and then he showed that it's the same thing as the nucleus of a helium atom. Now he didn't know that there was a nucleus, but if you take that and you put it in a place where it can pick up a couple of electrons, it turns out to be helium.
So at this point, when he's doing this experiment, he's thinking of alpha as little pieces, and the gold is bigger pieces.
Right. So he's thinking that the plum pudding thing is the gold of these plum pudding things. The alphas are coming out. They know that they're coming out at extremely high speeds, and they know that they're very tiny. And more than that, what it is, they don't really know.
So an alpha particle is very heavy or very dense?
It's pretty light. It's very dense.
Okay.
So, right. Okay. So you need some massive thing at the center in order to have an alpha particle come in and bounce off. Right? So an alpha particle is relatively light. You need most of the mass of the gold to be concentrated in a point, and you need the alpha to hit that and come back to explain these results. So Rutherford's the guy who, the cartoon atom that everybody sees, Rutherford's the guy who invents that. So you picture the atom sort of like a solar system. You have a nucleus that's positively charged. You've got electrons going around the outside. All right. The nucleus has to have like 99.9% of the mass. We know about how big an atom is. An atom's sort of 10 to the minus 10 meters, 1/10 billionth of a meter. The nucleus, based on these results, you can say the nucleus has to be about 100,000 times smaller than that. Right? 10,000, 100,000 times smaller. The evocative phrase that somebody uses is it's like a fly in a cathedral. All right, it's actually the name of a pretty good book about experiments done in Rutherford's lab. So this is Rutherford's model of the atom, which has a tiny problem, which is it can't possibly work. All right, because we know that light is an electromagnetic wave. It's made by moving charges. Well, this has got a whole bunch of moving charges. Right? You've got this nucleus, you've got this electron whipping around the outside of the nucleus. Well, that electron whipping around the outside of the nucleus, that ought to be making a whole bunch of light. Right? It ought to be spitting out X-rays in every direction. But if it was spitting out X-rays in every direction, the electron would be losing energy. It wouldn't be whipping around as fast, and it would sort of spiral into the nucleus and crash. So that can't work. Right? That manifestly does not happen. If I get an atom, it's not spitting out X-rays everywhere, and it doesn't cease to exist after a very short time. Right? So something else has got to be going on. And this is where quantum physics really takes off. With Niels Bohr in 1913. Bohr is a Danish theoretical physicist who has actually worked with Rutherford for a while. Bohr puts out the first quantum model of an atom, and he says, okay, there are certain special orbits for which we just suspend the moving charges radiate rule. We're just going to say that for these particular orbits, electrons in those orbits just don't emit any radiation. Why? Don't ask. All right. But he says, if you do that, and you say, well, when do atoms actually emit light? They absorb or emit light when the electron changes between two of these states. Two of the orbits.
Why would it do that?
Well, because some light came in and gave it some energy, or it has some extra energy, and it gets rid of that by spitting out some light. Okay, so it can jump back and forth between these, and the particular frequency of light that you get depends on the energy difference through this rule that Planck introduced and through the same rule that Einstein used to say what's the energy of one photon. Okay, so the photon, the frequency of the light that comes out, F, is equal to the difference in energy. Okay, and you have to stick in a constant here to get the units to be right. The constant that you put here is Planck's constant, h. So h times the frequency is an energy. That energy is the difference between the states that the electron jumped between. Yeah.
So is this have a direction? So is the inner shell have more or less energy than the outer shell? So if you jump up a shell, you emit. You jump down, what happens?
So sort of conceptually, the way that people usually draw this is as if the lowest energy state is the one in the center, and they have higher energy as you go out.
So when you're going from this higher energy state, you're drawing to a lower energy state.
Right, so I've drawn this going from a high energy state to a low energy state. The atom has lost energy. That means it gives up some energy that travels off as a photon.
So one would expect that if you jump from a low energy to high energy, the higher energy would not emit.
Right, so to go from low energy to high energy, you can do that by absorbing some of the light. So if you shine in light at the same color, the low energy state can go up to the high energy.
So I'm sorry, just to back up a minute. So Planck sitting around in his house one night came up with this seemingly almost random number, and now it's being applied somewhere else, and it works there too?
Beauty of physics. Right? Like all of these things turn out to be connected.
That's kind of crazy.
Well, they're actually all related to this. They're all relating to the same thing, right? Everybody who's worked with this has been concerned about what is the energy contained in a little bit of light. So Planck was saying, well, let's say we got some energy in these oscillators. They're going to spit out the light. And we're going to say that that's quantized, that only comes in discrete chunks. And Einstein says, well, we have this situation where electrons coming out in the photoelectric effect do this weird thing where it seems like they have some minimum energy. Let's say that it's not the oscillators, it's the light itself that is carrying discrete quantities of light. And now Bohr is picking up on that and saying, well, if you've got light that behaves like a particle that carries off a discrete amount of energy, maybe this absorption and emission is related to changing of energy of electrons inside the atom, and then that's got to be discrete. All right. And he says, well, so we have these special orbits. How do we decide which orbits are special? He says, well, there has to be something that has an integer in it, because the formula that describes the frequency of light emitted and absorbed by hydrogen has these integers, these n1 and n2 that show up. So we've got to have something that has an integer associated with it. And the thing that works is to say that the angular momentum of the electron going around the nucleus is an integer multiple of Planck's constant divided by 2 pi. So.
Angular momentum, are you talking about the path of the orbit?
Right, so angular momentum is basically, linear momentum is mass times velocity. Right? So if you're going in a straight line, you have this quantity that's associated with your motion that's roughly speaking your mass times your velocity. And it's sort of pointed in that direction. All right. If you have something that's spinning, there's a related thing, right? If you see, ice skaters, if they spin around with their arms out, they spin relatively slowly. They bring their arms in, they go faster. That's related to this quantity of angular momentum that has to be the same. It's associated with something that's spinning. If you think about that for something that's going in a circular orbit, the angular momentum is the momentum, the mass times velocity, multiplied by the radius of the orbit. So you just stick that in there. That gets you so this tells you, the mass, the m here is the mass of an electron. That is what it is. All right. And what Bohr says is these special orbits are, the velocity times the radius of the orbit has to be chosen so that you get an integer multiple of Planck's constant. Right. So these aren't really perfectly well, it's not a perfectly well-defined radius that you have. It's, for a given radius, it would have to be moving at a certain speed. All right. So these, drawing these cartoons are a little fishy. even at the Bohr model stage.
H over 2 pi doesn't give you an integer value.
No, the n is an integer. So
Right.
h over 2 pi is what it is. It just gets you the units. So there's some fundamental angular momentum that is h over 2 pi.
So if you do an integer times h over 2 pi, you get some fractional value.
Yeah, you get some number, but it's an integer number of h pi's.
Oh, okay. I see
So.
what you're saying. Sorry.
Yeah.
It's
So.
almost one. That's what's weird about it.
So they're actually really small for the most part.
Isn't there some alternate formulation where the special orbits are an integer number of particle wavelengths?
I'll get there in just a minute.
Okay.
But yes, that turns out to be right. So this is Bohr's model. If you take these equations and you sort of do some classical physics, people know how to do very well. You can use this to generate exactly the formula for the frequencies of light absorbed and emitted by hydrogen. So this works absolutely brilliantly for hydrogen. Works in the visible, works in the UV, works in the infrared. You get the right value of all the constants that show up. Everything works great. Bohr had also been thinking about X-ray spectra. What happens, if you slam electrons into a material really hard, then they'll spit out X-rays, and those X-rays tend to have characteristic energies, and you can sort of use this sort of discrete electron state model to explain that and roughly explain what frequencies you get out for the X-rays. It gives you a wonderful explanation of chemistry. Right, if you've ever taken chemistry in high school, you talk about the periodic table, and you're filling electron shells, and you get 2 electrons per shell, and all this wonderful stuff. Explains why the rows and columns of the periodic table are meaningful. That's all terrific. Sort of kind of works for heavier atoms. If you try to explain helium with it, you can't get all of the lines in helium. But if you look at ionized helium, you take 1 electron off of helium, then it works great. And it's the same thing for any other atom. If you strip off most of the electrons, you can get a spectrum out that you can explain beautifully with the Bohr model.
So when you said it explains all the lines, are you talking about the orbits, or are you talking about
The frequencies.
Okay.
Yeah. So lines is sort of the jargon term, because you send the light through a slit, or you make a long narrow lamp like this, and then when you look at the pattern, you see a set of discrete lines. So.
Explains the spectrum.
Right. So the whole spectrum of hydrogen is explained perfectly by this. Sort of kind of get some of the other atoms. And there's a period where people spend a lot of time doing sort of refinements of this. And so if you make the orbits not circles but ellipses, you can add some extra bells and whistles, and you can be a little more successful explaining other things. The problem with this is there isn't a particularly good reason why you would want those particular orbits to be special. And so the question is, why would that be special? And this is where things get really strange. So 10 years later in France, this is around 1923, 24, this fellow is marvelously French looking in this picture. His name's Louis de Broglie. There's a lot of discussion about how to actually pronounce his name, but it's I'm told that it's de Broglie, but there's sort of a gargly thing with the oi that you have to be French to do right. So anyway, he's a PhD student, and he says for his thesis, well, look, light waves have particle nature. Maybe we should say particles have wave nature. All right, which sounds completely crazy, but you can make a very simple equation here. You can say that a material object should have a wavelength that's equal to Planck's constant h, again, divided by the momentum of that particle. And if you do that, this is just a rearrangement of, if you talk about light as a particle, you can say, well, each of those particles has some momentum. What's the momentum? It's h divided by the wavelength. So it's just the same formula rearranged. If you say you make that same identification, then there's a beautiful mathematical symmetry to this. All right. So it's a wacky idea, right? Why would you do that? We don't see things, material objects having wave properties. But the reason you could do that is that this explains the Bohr model in terms of what you just mentioned, that if you do that, this gives you, connects the momentum and h to a wavelength. And you say, well, okay, then what's the integer part? The integer part is the special orbits end up being orbits where an integer number of waves fit around the orbit. So this is an imaginary orbit. If I start, say, right here at the top, right, I've got a wave here that goes down, then up, then down, then up, down, up, down, up, down, up, down, up, down, up, and comes back to where it started. Right? If I go all the way around this, there's a wave wrapped around this circle that comes back to exactly the place that it started. So there's an integer number of wavelengths that fit in here. What is it? So it's 1, 2, 3, 4, 5, 6, 7 oscillations of a wave wrapped around that circle. Right? So that would be one particular, that would be n equals 7 for this particular atom, whatever it is. So if you do that, that's sort of a physical underpinning that would justify why are these integers showing up in Bohr's model? Why are these the particular rules that you use to pick out what are the special orbits?
So that's the frequency that's emitted by a particular orbit?
Now imagine this as, so the colors are just to look pretty. I grabbed this off Wikipedia. Imagine this as the electron. Okay, and the electron has a wave associated with it, and it goes up and it goes down, and as it's going around, and it eventually comes back to exactly where it started.
So it's like a spiral graph.
Yeah. Yes.
You have an electron that has effectively living as a circular wave around the nucleus, and you have a shell that allows, like the first shell allows two.
Mm-hmm.
So you have two electrons. Do they effectively reflect the amplitude of that waveform?
Talk about that. So the what's waving is sort of the next part of the talk. It's a very deep question. I can't give a really short answer to it.
Good
So,
deep questions I cannot answer.
so I mean, we could sort of answer it, but I've got some stuff on that a little later. So this is de Broglie's idea. Okay, and he writes this up, proposes this as his PhD thesis. There's a story that may or may not be true that he submitted this, and the university where he was at didn't know what to do with it, and Einstein happened to be visiting at the time, and so they showed it to him, and he read it and said, "This is brilliant," and so they said, "All right, we'll give him his PhD." So the idea, this kind of thing where you have a wave that comes back to exactly the place where it started is referred to as a standing wave. It means that you have this orbit, the peaks and valleys of it will be sort of fixed in place because every time around, it's going to end up in exactly the same place.
And that's called a special.
And that standing wave is. This is a phenomenon that's very general, happens with waves. It's what if you play a stringed instrument, okay, the strings on a guitar or a violin, each string has a particular frequency it vibrates at because you've fixed the two ends of it and it can vibrate in the middle, and that frequency is associated with a wave that's the length of that string. It's actually twice the length of the string is the fundamental frequency. So there's this standing wave physics shows up. It's something that's very familiar. Everybody's kind of happy with this. But it requires this wacky business of electrons behaving like waves, which is a really strange idea. But once you have the idea that an electron might behave like a wave, you can go and look for it. Right? And de Broglie's thesis is in like 1923, 24. By 1930, physicists had very concrete evidence that electrons behave like waves. And these days we have a really beautiful demonstration of this. This is from Hitachi. They made a source that spits out one electron at a time. And then they're shining this on, they're shooting those electrons at a fluorescent screen. And each time an electron hits the screen, it makes a little dot. All right, so you've got all these little dots. And this is just a video compilation of just doing this over and over and over again, one electron at a time at the screen. But between the electron source and the screen, they have an array of slits. All right, and so the electrons are passing through slits. And what you see is each individual electron is detected at a particular instant, at a particular position, making a single dot on the screen. But if you repeat this over and over and over and just add each dot to the picture, what you see is this pattern of bright and dark stripes. All right. There are places where you detect lots and lots of electrons, and there are other places where you detect very few. All right. And it's almost clear in the black and white still images. So, right, each individual electron makes a dot. Right. The pattern of their arrival times and positions seems pretty random, but if you add up enough of them, right, you get this pattern of bright and dark stripes. And this pattern of bright and dark stripes is exactly the diffraction phenomenon that you see, that Steve showed you with the laser pointer and with the laser in the box here. You get this pattern of bright and dark stripes that's characteristic of wave behavior, but each of these electrons is detected like a particle at a particular place at a particular time.
Independent of each other.
Completely independent of each other. You could see in the early part of the video that you get a dot, and then a little while later another dot, and then another one, and then it's not that they're coming in lots of them at once. It's really one at a time, and yet you get this wave behavior.
So before, when Steve had his thing up, I asked the question that there was a relationship between the frequency of the light and the dispersal of the So I'm going to ask the same question here. Is there a relationship between some unknown frequency and this diffraction?
In this case, so what determines the spacing of the peaks in the pattern is the wavelength of the electron, and the wavelength of the electron is related to its momentum. So they can choose how fast the electrons are moving when they come out of the source. I don't know how well they control that, but they come out at some particular speed, and they know what the speed is. That speed, right, is the velocity of the electron, which gives you the momentum of the electron, which then gives you the wavelength associated with that, and you can predict this pattern. Yes.
Why do you need two slits in the barrier for this to be visible? Why two slits? Why not 3 slits?
I think this is actually, I am not 100% sure. I say 2 slits on here. I'm not sure it's 2 and not a million. Okay, it says double slit. So this may actually be 2. You need more than one. You can you can do it with one. You get a pattern that like Steve used the hair. So a single object will give you some diffraction. You get a really clean pattern if you do it with 2, and the math to predict it is easy. So that's sort of why everybody talks about this in terms of 2. The peaks if you use more slits, the peaks get more distinct. So you can, so those diffraction gratings that I handed out earlier, those are, that's thousands of slits per centimeter on those things. So you get really widely separated peaks in that, and so that's why those are useful.
Does it depend on time or the number of electrons to wait for that to happen?
To build up a picture like that, it's just number of electrons, and how long it takes is a question of how fast you fire them in. So if you,
numbers that make the pattern,
yeah,
not time.
yeah, it's so the pattern that you have here is a wave phenomenon that you can explain by saying I have an electron wave that's coming in with a particular wavelength. It passes through both of these slits. That produces a probability distribution on the far side that tells me what's the probability of finding an electron at a particular point. And then doing this a bazillion times is just revealing that probability distribution. right? I can't measure a probability distribution by detecting one particle, but I can, in order to measure a probability distribution, I need to repeat the experiment many, 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 many times. And when you do that, then you trace out. But each of these individually is doing this wavy thing before it reaches the screen. It's when it reaches the screen, you get it at one point, and one point only. Yes? Yeah. Yeah. And that's just a general result. What determines whether you have a bright spot or a dark spot is the difference between the lengths of the paths that they take to get there from the two different slits, and they're exactly the same in the center, and that gives you a bright spot. So, okay. This is a really beautiful experiment. This Richard Feynman famously in the 60s said that this experiment, he was speaking of it as in conceptual terms, but the idea of doing this double slit with electrons contains the central mystery of quantum mechanics. Like all of the weird stuff is right there. And so.
Now, in the previous light experiment, when you saw this on the thing, it looked like, maybe I misinterpreted it from my distance view, that there was a brighter distribution, and as you went away from the center, they became dimmer.
Mm-hmm.
Now, that does not seem to have changed it.
It sort of does if you look at this. The bright spots on the outside are a little less bright than the ones in the middle.
Okay.
That's a technical issue. It has to do with how narrow you make the slits. The narrower you make the slits, the more the waves spread out, and the wider the pattern you get on the far side. So there's this dropping off of intensity. It's just the waves that come out don't spread perfectly in all directions. They sort of go in a cone, and the width of that cone depends on how narrow the slit that you pass through is.
So what do the slits do to create the picture? Like, what do the slits do to the electrons to create the picture of the wavelengths?
Right.
As opposed to no slits at all.
Right. So what you're doing, it's the same thing that happens with water waves. You're really saying there's a barrier where there are no waves, none shall pass, right, through the solid part of the slit. And then there's a little region where you're making waves. Now, the little region where you're making waves, it makes waves that want to go out in all directions. They don't quite manage all directions, but they want to go out in all directions. And then they expand from there as if it were just a single point emitting, sending out waves. So you can make a double slit type pattern in a tank of water by taking two fingers and just doing this, and or you drop two rocks at the same time. When they hit, you get waves going out in all directions from those points. Those waves overlap and interfere with each other.
So the particle is going through one slit or the other, but the wave is going through both of them at the same time?
That's one way to think about it. You could also say that since the particle and the wave are really the same thing, you could say that the particle is going through both slits and behaving like a wave as it does. There's a way to formulate all this where you say there's a wave that sort of carries the particle along, and that wave passes through both slits, but the particle only goes through one. And that gets complicated, but you can do it that way, but you have to add this extra wave that's associated with things. Or you can say it's all, it's all just waves, and the particle thing that we're seeing is a sort of consequence of the way that we measure stuff.
There's an overall issue that there is no generally agreed upon explanation.
Yeah, and this is the last session that's on there. And I'll talk a little bit about interpreting the wave function, but that there are these, the math of how you calculate these things, everybody knows how to do, and everybody agrees on how to do the calculation. What the calculation means, how you interpret, where is the electron between leaving the source and hitting the screen. What you say is happening in that period is a topic of much debate.
Question? Back in the time of Bohr and Royal, was there any attempt to explain the timing uncertainty as to why does an electron in an excited state decide now
So this idea of spontaneous emission is the term for this. Right? You take an atom, you put it in a high energy state, and after some time it will spontaneously drop down to a lower energy state and emit some light. That's an incontrovertible experimental empirical fact. Explaining why that happens turns out to be really hard, and I think people don't get like a really rigorous explanation of that until might even be into the 60s, like Glauber and somewhere in there. So like Einstein just treated it as a fact. It's like, why does this happen? It does. So let's go with that and see where we get.
Is it explained even now?
Yeah, now there's a good rigorous explanation of how you do that. It has to do. The usual hand wave that people give is you say it has to do with fluctuations in the vacuum, and so there's at quantum mechanics tells you can never get rid of all of the energy at a particular wavelength. So you have light waves of some particular wavelength. You can have 1, 2, 3 excitations of that. One photon, but 0 photons turns out to really leave behind half a photon worth of energy. And then you say, well, there's like this half a photon, so that triggers the atom to emit at that particular frequency. And
But is that still a probabilistic explanation?
it's a probabilistic thing, yeah. It's all you can say is you can say what the probability at any given instant of an atom emitting a photon is, but you can't say it's definitely going to emit now. But we can measure that because we can take, you can take 1 trillion atoms and excite all of them and then look at how many of them emit over time. And that predicts an exponential decay, and we see beautiful exponentials when you do that.
Same sort of exponential as nuclear decays?
Yeah, it's exactly the same thing.
So interestingly, if you did the classical calculation, where Chad said, classically we expect electrons to radiate energy, so you couldn't have any special orbits that decay away. Calculate how fast do they lose energy. It's basically the same as what happens quantum mechanically. Just quantum mechanically, it's a random process what it does. So I take 1 trillion atoms, and I see this exponential decay. If I calculate classically how fast does the energy come out, it's the same. But in fact, the photons are coming out at random times, discretely. But if I average over everything, it kind of somehow it still knows what the classical physics is.
Trying
Yeah.
not to think about how which atom knows when to do it.
Exactly.
Yeah,
Go
exactly.
with the curve.
And that's the whole God playing dice, Einstein's famous snide comment.
Doesn't it kind of put a whole new spin on what we consider to be random?
It sort of defines what we consider to be random. So the best sources of random numbers that we know of, if you want a string of ones and zeros that you can guarantee to be random, is take some atoms and look at their decays, and that it's, as far as we know, it is absolutely impossible to predict when any particular one will go. So you can just use that as a random number generator.
Which is why some true random generators use the cosmic background radiation.
Exactly. So one of the ways that you make random numbers is you take a radio telescope and point it at an empty area of the sky and just look at junk that's coming in, and what you're seeing is sort of random arrivals of photons, and you convert that to ones and zeros, and as far as we can tell, that's as perfectly random as you can get.
But it may have something to do with stuff we don't understand.
That's always a possibility. You can do sort of statistical tests, and people have, because people use this sort of thing as like the basis of codes. You want to generate some random numbers, they'll do that, and to try and convince themselves that there really isn't a hidden pattern in that. There are statistical tools you can do to take those strings of numbers and say, is this really random, or is it pseudo-random? Is there actually a hidden pattern? And to the best of anybody's ability to test that, there isn't a pattern. So, they do the same thing with like digits of pi, and E and those sorts of things. You can do these tests to see, is it truly a random pattern, or is there a pattern hidden? As far as anybody can tell, there's no hidden pattern. What's the book? It's Sagan's Contact. Has the, they're going through digits of pi at the end, and at some particular place, it makes a pattern, and there's hidden order in the universe, right? Nobody's found that yet, but people look for it.
It's where the dark matter is.
Mm-hmm. All right, so this is for electrons. You see this wave behavior of electrons. You can do this with atoms. I didn't have a slide. Atoms. This is Buckyballs. These are molecules. So these are soccer ball shaped carbon-60 molecules. And this is an experiment where they're looking at how many molecules arrive at the detector at a particular position. And you see this wavy pattern that's exactly a diffraction pattern. They're shooting these buckyballs at an array of slits, looking at the pattern that comes out, and you see this wave behavior. So this is 60 carbon atoms. People can do even better than that. This is doing interference of very big molecules. So these, I don't even know what the names of these things are. They're some unpronounceable chemical thing. What I can tell you is that this one right here has 430 atoms in it. And it produces a signal when they send it through a diffraction grating. It produces a signal that looks like this, that has this wavy stuff happening. That proves that these 430 atom floppy organic molecules are in fact behaving like waves if you do this experiment properly. So everything behaves like waves, right? Electrons have wave nature, neutrons have wave nature, protons have wave nature. Whole, big floppy organic molecules have wave nature.
Curiosity, if you have a big floppy organic molecule like that, you aim it at a slit, do they have a finite size that the slit has to be in order to fit them through as a particle, or does some wave magic happen when it goes through a smaller slit?
Yeah, when they do these specific experiments, this is a group, I don't have the names on here, but this is Anton Zeilinger's group in Vienna. Or by this point, it might have been taken over. There's a guy named Marcus Arndt, who's sort of his niche in physics is doing progressively larger molecules and demonstrating that they have wave behavior. This is not actually, I believe there isn't a physical grating here, so they're not shooting these big molecules at a physical barrier. They use standing waves of light to produce the same effect. And it turns out to be, when you do that, then you're not gumming up your slits with the molecules that didn't make it through. So they all make through, just some of them get steered off in weird directions.
Electrons have mass, right?
Yes.
And photons don't.
Right.
So why do they both behave the same in the particle or in the slit?
So photons don't have mass, but they carry energy with them, which means that they have momentum as well, and so in some sense the fundamental quantities to think about are energy and momentum.
And the mass is sort of irrelevant.
And so for material things, the mass is related to the energy and to the momentum, but for a photon, it's it's always moving at the speed of light, and it always has particular momentum and a particular wavelength. So there's a nice symmetry between them. It's not a perfect symmetry because material things have mass, and so that changes things a little bit. But so when you incorporate relativity into it, it gets a little more complicated. But it does work. All right. You can also look at doing this with big separations. So these experiments with those floppy organic molecules, they're talking about diffraction gratings that are the spacing between the slits is nanometers, right? And the spacing between the particles as they go through different paths is very, very small. You can also do this where you separate the waves by a large amount. And so this is Mark Kasovich's group at Stanford has these experiments. They have a 10-meter high tower that they have a vacuum chamber in, and they take a ball of atoms at the bottom of it and they toss them up, and it takes a couple of seconds to go up and come back down. And when they do that, they can separate the atoms into two balls and then bring them back together and recombine them. And when they do that, they see an interference pattern. And so this is a picture from a few years ago. This is at the top of their apparatus. They can take a picture and they could see that there's a lump of atoms here. There's a lump of atoms here. They're separated by about 1.5 centimeters. More recently, they do this and they can separate them by 0.5 meters. So they can separate them by 1.5 feet. And then when they bring them back together, they see them interfere and behave like waves. So you can show that atoms behave like waves, even if you take them and pull them 0.5 meter apart and then bring them back together, that still produces an interference pattern that they can use to make very sensitive measurements. So, so the obvious question to ask maybe, so I'm asserting all of these things behave like waves. So why don't we see that? All right, so I talk about dogs and physics with dogs. So if I have a dog running across the yard, this is telling me that there ought to be a wavelength. Right? That dog has wave nature. Okay, right? Dog also has Buddha nature, but right. So the dog's running across the yard. It should have a wavelength associated with. Why do we not see that? All right, and the answer is that Planck's constant determines what the wavelength is. And Planck's constant's a really, really small number. It's 10 to the minus 34. So if you take sort of a reasonable mass for a dog and a reasonable speed at which a dog might be moving, you can calculate what the wavelength is, and you get a ridiculously tiny answer. All right. So what do I mean by ridiculously tiny? So if you imagine an atom, okay, you take an atom, your sort of Rutherford Bohr solar system atom, all right, and you imagine taking that atom and blowing it up so it's the size of the actual solar system, okay? And along with it, you blow up the wavelength of the dog, all right? The wavelength of the dog compared to the now solar system-sized atom would be the width of one atom within that solar system. Okay, so the wavelength of a dog, to the size of an atom is like the size of an atom to the size of the solar system. Right, the dog running, right? So if you're considering the dog as one quantum object and saying, what's the wavelength of that dog? The answer that you get is so ridiculously tiny that, compared to the size of an atom, it's like that atom compared to the size of the solar system.
So if you were drawing that as a sine wave, it would just look like a big blob, because they're so close together, the waves.
Right, right. The wavelength, it would just,
like an ink blob.
yeah, you wouldn't be able to see it at all. All right.
What's the size relationship between the wavelength of our hypothetical dog and
I actually have a marker here. So the rule is the wavelength is equal to Planck's constant divided by the momentum. So this is Planck's constant divided by the mass times the velocity. So Planck's constant is 10 to the minus 34. The mass of a dog is like 10 kilograms. The speed of a dog, casually is like a meter per second. So, you're looking at like 10 to the minus 35 meters for sort of a casually moving dog.
So that means that bigger objects may actually have smaller wavelengths.
Right, so the bigger the object that you're dealing with, the smaller the wavelength
So if,
is.
hypothetically, I know this is completely impossible, if you tried to throw stars through an interference pattern, you get something.
Yeah, so, anything like bigger than a dog is going to have an even smaller wavelength.
I was using that as a completely ridiculous.
Yeah, that's actually a thing, right? So you see pictures of tiny things. It's always an electron microscope image, right? The reason that you use electron microscopes is you can do optics with electrons, treating them like waves. All right, and you can make an image the same way that you make an image with light, but because an electron has a mass, and a photon doesn't, the wavelength of the electron is, an electron with a convenient energy to work with has a wavelength that's much, much shorter than any wavelength of light that we can easily work with. And so you can make images of things that are, the wavelength of the thing you're using to make the image determines the smallest thing you can take a picture of. So you use an electron microscope because the wavelengths of the electrons are really, really tiny, and that lets you take images of really, really tiny things. And people do, for materials things, people do diffraction with neutrons using the wave nature of neutrons, and neutrons are 2,000 times heavier than electrons, so the wavelengths are even shorter.
So, I mean, I'm just thinking about this picture of the stop moving.
Mm-hmm.
If you kind of, drew out, or like what it looks like when a dog is running,
Mm-hmm.
I mean, like, you could definitely trace a kind of, like a wave-like movement. Do we not consider that to be related at all to, like?
Oh, you mean you're not talking about like the dog sort of bounding up and down kind of thing? No, that's not going. That's just the physics of the way they run that makes them go up and down. Now the wave the sort of wavelength I'm talking here would be, if you wanted, my dog always wanted to be able to go around both sides of a tree and trap a squirrel on the between herself on the other side, and it's to do that. So the sort of quantum wavelength is related to how easily could you observe something going around both sides of an obstacle and producing an interference pattern on the far side. And the answer is, for as short a wavelength as the dog would have, and compared to the size of the tree, it's just not going to happen. So it's the wavelength that we're talking about here is a wavelength of, the associated with the wave function of the dog. And if you tried to do an interference experiment with sending a dog through multiple slits, that's the wavelength that would show up in it. What's that?
Is it theoretically possible, though, a non-zero probability?
Yeah, it's so ridiculously small. Now there are theories where, the reason I said that there's this fellow in Austria who, has made a nice career out of doing interference with progressively bigger things. The reason for that is there are some variants of quantum physics say that, there might be sort of a maximum size. There might be a point beyond which some quantum gravity thing happens that prevents you from making superpositions of, from seeing wave behavior in things above some mass. And so people are working on just, keep pushing that limit up, and maybe eventually you reach a point where something ought to happen. And nobody's got there yet. But it's extraordinarily difficult to do. The things that they do to get these organic, to get a usable signal out about these organic molecules is really impressive. So.
Will you be talking about quantum tunneling at some point?
I don't think I talk about tunneling specifically. I don't know if anybody. I mean.
Save that for some random question.
Yeah, I can draw a cartoon of it a little later when I talk about wave functions. So it sound or has.
We still got more.
So okay,
I don't know.
yeah, keep going. Okay, so all right, so so I'll go on to talk about wave functions, I guess. But the sort of take home on matter waves, and then maybe we'll take a brief break to refill coffee and whatnot. So take home is, material objects have wave nature. This is not something that people dreamed up while, smoking controlled substances. It's a really strange idea, but it follows from a chain of experiments. And this is experimentally confirmed up to fairly heavy organic molecules. They keep talking about, they float the idea of doing like viruses, though I don't think they've ever actually gotten that to happen.
For
But,
science fiction,
But that's one of those things that
Somehow we think of a virus
as being special, and yeah, but yeah, that's one of their stated goals, is to move up to living cells at some point, if they can figure out a way to shoot those through diffraction grating. And then the people ask, is there a limit to the size of how big, how heavy an object you can have and see wave behavior, or how far you can separate them and have wave behavior show up, and people are pushing on all those limits, and nobody's found an upper limit yet. So.
You say how far you separate in time or in distance?
In space.
In space. Okay.
So like the Kasevich thing, where they have it, I say it's it's a lump of atoms here and a lump of atoms here. That's when they take a picture, what they see is a lump of atoms here and a lump of atoms here. But really what that is each atom is here and here, has some probability of being here and some probability of being here at the same time. And when you take a picture of 1,000,000 atoms that way, what you see is 500,000 of them here and 500,000 of them there. But each one individually is split between those two locations. And so, they have that's 0.5 meter. I'm making it a little farther than it is, but it's like this far apart. You could put your hand between them, right? If you could get inside their vacuum system, you could physically impose a barrier between them with no problem, and then they bring them back together and they still see wave behavior. They still see an interference pattern that, the interference that you see depends on, how long were they separated, how fast are they moving, and that sort of thing. But they see exactly what they expect. So there is some question about, is there some limit? You take an atom and split its wave function into pieces that are separated by, is there some maximum spatial separation between those pieces that you can have? And they're working on testing that. It's a really neat experiment. So I'm all about. I used to work for Mark too, so I think the stuff that he does with that is super cool. But, any other questions?
Like a metaphor. There's no divorce possible.
Mm-hmm.
Because as soon as you stop doing what you're doing, they get married again.
I guess in a sense, you have to work a little.
But they get back together. Right?
Yeah, you have to work a little hard to bring them back together, right? There's some counseling involved in the process. They have lasers that they use to launch these atoms upward, and then they use a series of laser pulses to cause them to separate and cause them to move back together, and then they do something to put them all back, in the state that they started in. So. Yeah, like I said, there's some counseling